Alternating series. So this is maybe something that you learned a little bit about in pre-calculus, and it's a very interesting type of series, I think, because it it just jumps around between kind of two different values, and it might settle somewhere, it might settle at two different places. It's kind of interesting type of series. In the last video, we covered the comparison tests, we covered the integral test, we covered the integral test estimation. And that was fairly effective. So the integral test is great for series when we have some sort of positive decreasing function. So the p series is a great example. Um, Additionally, we use the comparison test. That's good when we have series that we know converge or diverge, and then we know that it's greater than some sort of series that doesn't converge or diverge, or we don't know, and then we can determine by using the comparison test. Well, the alternating series has its own test and its own estimation theorem. We're going to cover that in this video. So let's get started. So an alternating series is a series that we have some sort of -1 to some power. So we index that power. So we have -1 to the n-1th power. So what does this mean? So as n goes up, n takes integer values. So we're going to be jumping between +1 and -1. Because if we have 1, -1 to an odd power, then that's going to stay -1. But if we have it to an even power, like -1 squared, well, it's going to be +1. So if we look at just the elementary fundamental alternating series, which is just -1 to the n, well, -1 to the first power is -1, -1 to the second power is 1, and then we keep jumping between -1 and 1, so we keep alternating, right? But then here in calculus 2, what we add is we add this funky bit here, this b sub n, and this b sub n is some other series that we attach onto it. This could be any of those building block series that we discussed in previous videos. That could be a geometric series or something like that. But it adds a little bit of flavor to our alternating series. So let's discuss that. So if we have the alternating series from n equals 1 to infinity of -1 to the n-1 times b sub n, with b sub n greater than 0, then, and we also satisfy that b sub n-1 is smaller than b sub n for all n, so that ensures that it decreases. And we also pass the limit test. So if we take the limit, of the sequence b sub n, and that equals 0, then we converge. Then the alternating series converges. So that's the test for alternating series convergence. Let's do an example to see if we get it. So let's determine whether the sum from n equals 0 to infinity of -1 to the n times n cubed over 3n cubed plus n squared plus 1, let's determine if that converges. Okay, so first what we need to do is we need to ensure that we have our b sub n. So let's separate out our b sub n. So our b sub n is going to be this guy in here, this fraction. So we get b sub n is equal to n cubed over 3n cubed plus n squared plus 1. Okay, so let's see if it decreases. So we do have that, we can see b sub n is going to be greater than b sub n plus 1, but also let's see if we converge. So we're going to take the limit. So we're going to take the limit from n, or as n goes to infinity, of n cubed over 3n cubed plus n squared plus 1, and we're going to take this limit as n tends to infinity. So this is kind of a throwback to our limits video in Unit 1. I think like video 4 or something like that. We were talking about how we take limits as n approaches infinity. So that's like an asymptote, a horizontal asymptote. We cover the rules that if we have the same degree on the top as the same degree on the bottom for leading order polynomials, we can just take the quotient of the coefficients, and that's our limit. Well, we have the same leading degree, so we have n cubed and we have n cubed there. So then the limit's going to be 1/3. So if we have a limit of 1/3, then that's not equal to 0. And for our series to converge, for us to pass the limit test, then it needs to be equal to 0. So then our series, the series from n equals 0 to infinity of -1 to the n times n cubed over 3n cubed plus n squared plus 1 diverges by the alternating series test. So we have a divergent series. Okay, but you could see what happens if we had a convergent series, such as if this went to 0, maybe if we raise the degree of this guy here to like 3n to the 4th, then that limit would be 0, and then we would have a converging alternating series. But we don't here, so that's a bummer, I guess. All right, so we also have estimation theorems for our alternating series. So let's say that if we satisfy the same conditions as in the alternating series test, so that was that b sub n plus 1 was less than or equal to b sub n, and then the limit as n approaches infinity of b sub n equals 0, then our series converges, so that implies convergence. And then we can say that the remainder, the absolute value of the remainder, is equal to the absolute value of the sum minus the nth partial sum, which is less than or equal to b sub n plus 1. Okay, I gotta say I'm not a super big fan of these estimation theorems just in their definitions because they're very hard to grasp. So let's do an example. So we're going to do example from Stewart section 11.5.4. So we're going to find the sum from n equals 0 to infinity of -1 to the n over n factorial to 3 decimal points. Okay, so how are we going to tackle this? So first we need to ensure that this converges. So if I take b sub n plus 1, so that's 1 over n plus 1 factorial, is that going to be less than 1 over n factorial? Well, yeah, because we're taking a larger factorial, and factorials grow maybe even faster than exponents. So yeah, that's going to be smaller. And what happens if we take the limit as n approaches infinity of 1 over n factorial? Well, yeah, n factorial grows faster than x squared or n squared. So and if 1 over n squared goes to 0, then 1 over n factorial definitely goes to 0. So we have a convergent series. So now what we are going to do is we're going to just write this series out. So our series is going to be, or a partial sum, or our sum is going to be 1 over 0 factorial minus 1 over 1 factorial, and so on and so forth, which is 1 minus 1 plus 1/2 minus 1/6, so on and so forth. Let's just take a guess at what's going to give us a somewhat accurate result, because this series shrinks really fast. So we don't even need to go very high to get an accuracy to 3 decimals. So let's take the 6th partial sum. So if we take the 6th partial sum, we're going to get 1 minus 1 plus 1/2 minus 1/6 plus 1/24 minus 1 1/20 plus 1 7/20. That's about 0.368056. Okay, so now let's find the 7th term. So the 7th term is going to be 1 over 5040. And 1 over 5040 is less than or equal to 1 over 5,000. So that's good. And that gives us, so 1 5,000 is 0.0002. So then we can write at the bottom that s minus the 6th partial sum is less than b sub 7 is less than or equal to 0.00002. And now if I take this series here, then we are going to, if I take this result here, then we are going to have no impact from this 0.00002. That's not going to impact our second decimal place. So that's an acceptable error for 3 decimal places. Okay, so that's the alternating series and the alternating series estimation theorem. So it's not too bad. In the next video, we're going to cover absolute convergence, the ratio, and root tests. Then we're going to be done with the tests for convergence, and then we can move on to the second part of Unit 11, which is really looking at how we can use series as tools to find solutions to problems that we might not be able to solve without them. All right, so we'll look at that later.